So friends, now we will discuss about the challenges of using HTS or high throughput screening for natural products. Now the first major challenge is the number of constituents that is present in an extract. We know that extract is nothing but a mixture of hundreds and thousands of compounds, and this mixture mayhem present one of the major problem in HTS. And it has been observed that the effect that is produced by the extract, we don't know whether that effect is due to a single compound or due to a synergistic effect of different compounds that are present in the extract. Second problem with the mixtures is sometimes extracts show a very good activity, but when we try to isolate a compound or we try to fraction that extract into different fractions, then that extract loses the activity. So again, we may get a false positive test in terms of extract, or we may get a false negative hit in terms of usage of extract for high throughput screening in a drug discovery process. And so in order to overcome such problem, extensive work has to be done in terms of purification, in terms of identification of compounds, in terms of removal of interfering compounds, and so on and so forth. So this process become more labor oriented and time consuming process. Second major challenge while using HTS in natural products is the pains. Pains are nothing but pan-assay interference substances or interference compounds. Now this term pain was given in 2003 and is largely defined as the class of compounds which have a common mechanism, or they basically interfere with the actual results of the assay, thereby they may give a false positive or a false negative test. And if we talk about paints, then polyphenolic compounds, flavonoids, quinones, tannins, such kind fatty materials, such kind of compounds that are commonly available in the extracts of natural products, and it has been found such type of secondary metabolic compounds, they interfere with the assays. Now we are going to discuss the elaboration or the effect of pains in HTS process in detail further. Then the third major problem of using extracts or using HTS in natural products is the stereochemistry. We know that compounds, when they occur in nature, majority of the compound they occur in the form of stereoisomers, and if we are using an extract, we won't be able to identify which isomer was responsible for the activity. We identify a compound, but we are not able to identify the exact isomer, and we then synthesize that compound. So what will happen that if we synthesize a compound, that particular compound, through a synthetic process, and we were not able to retain the stereochemistry of the compound that was present under natural conditions, then we may not get the exact biological results which we got in the HTS process. So again, whole of the process will lead to a false positive hit in case of stereochemistry. Then, since extracts which we are going to use in HTS process, they require lot of preparation steps. We have to either dilute the extract, we have to reconstitute the dried extract in a suitable solvent. So such kind of steps also lead to error, and not only error, but such kind of steps sometimes they also degrade the constituents that are present in the extract. One. Second, solubility issues may occur because extract contain compounds ranging from non-polar to the polar compounds, and while reconstituting that extract into solution form, if we are not using an appropriate solvent, which dissolves both non-polar as well as polar compounds, precipitation of insoluble components may occur, which will again interfere with the results of high throughput screening. Then variability and reproducibility of the raw material that is used to prepare the extract. We know that the environmental conditions, the geographical location from where the raw material is obtained has a major impact on the composition, chemical composition of that particular material. And therefore, if we get a raw material of different chemical composition, again the results will not be reproducible. Now, when we talk about the errors and degradation, say for example, we are using an extract wherein the compounds are susceptible to oxidation, and we obtain that extract in a dry form and then we are trying to solubilize it. So, as long as we expose that extract to natural environment, the oxidation of constituent will occur and it will degrade. One, if we are not using the suitable solvent for dilution or reconstitution, sometimes solvent also lead to the degradation of those compounds, or a longer exposure of the constituent to a specific solvent may produce some new compounds which we call them as artifacts, which were not originally present in the extract. Again, this will hamper the reproducibility of your process. So, these were few challenges which one faces while using HTS for natural products. Next is multiple mechanisms or multiple pathways that are being followed by the constituents of natural products to exhibit the effect. Now, we discussed that the extracts or the fractions are nothing but they are combination of hundreds and thousands of compounds, and it has been seen that sometimes these compounds they act synergistically to exhibit their biological effect. Now, when such kind of synergism occurs, it is very difficult to identify a single molecule that is responsible for the activity. Second major problem comes when we are looking for a specific outcome and some of the molecules follow a specific path to reach that outcome, whereas the other molecules, because of different chemistry, they follow a different pharmacological pathway, molecular pathway to reach the same outcome. Again, here we are going to get confused which was the molecular, what is the exact mechanism of action of this particular drug. So, this is another aspect, this is another type of problem which one faces while handling natural products in HTS. And last but not least is the concentration on which an extract is to be evaluated, because in HTS normally we evaluate different compounds on a single concentration and then we see that which type of compound, which compounds they act more effectively on that particular concentration. Whereas in case of natural extracts or fractions, since so many compounds are present in either in extract or fraction, evaluating that extract or fraction on a single concentration may lead into the losage or may lead into the loss of the compounds which have a very narrow therapeutic concentration index or window. If the extract is evaluated at a specific concentration which is having sufficient amount of the active molecule, then that extract will exhibit activity, otherwise that extract will not exhibit that activity and we may lose that particular active compound. So, these were few of the problems or challenges which one faces while handling natural products in HTS. Now, coming back to the pains, which is the major hurdle in the usage of HTS in natural product, that is pan-assay interference substances or compounds. So, as we discussed that these compounds may lead to false positive or a false negative results when we are using HTS. Now, there are different mechanisms by which these pain compounds they produce false positives or negatives. First mechanism is the photochromic properties, or we can say that the compounds can be fluorescent or they can be fluorescent quenchers. And since though I am going to discuss this mechanism in detail with suitable example, but briefly in previous lecture we discussed majority of the assays, they are dependent on the outcome that is measured in terms of fluorescence. So, the natural compounds which are fluorescence emitting compound or the compounds which inhibit the fluorescence, they might interfere with the exact outcome or the results of the assay. Second mechanism is the aggregation. We have seen in case of natural compounds that because extracts and fractions, as I told you, that they contain hundreds and thousands of compounds which also interact with each other, and once they interact they tend to form aggregates, and these aggregates again interfere with the results. Third mechanism is by the reactivity with the biological bioassay nucleophiles such as thiols and amines. We will discuss ahead that there are a class of natural compounds which have specificity for thiols and amines. They react with these thiols and amines and produce specific outcome which interferes with the HTS results. Another is redox activity. Certain compounds have high redox activity and they produce certain free radicals which cause damage to the DNA or RNA or to the protein molecules that are involved in the study, thereby leading to a false positive or a negative test. Photoreactivity is another mechanism. Metal chelation is a very common mechanism observed in natural products, because natural products are so complex, they form chelates with the metals, and once this type of chelation occurs, they can interfere with the protein conformations, they can interfere with the assay reagents, thereby overall altering the outcome of the assay. So, coming on to the first mechanisms, that is fluorescent molecules, or I will say photochromatic effects. So, we discussed that majority of the assays, they involve fluorescence measurement as an outcome of the assay, and natural product extracts may have compounds which have their own fluorescence. For example, coumarins, under UV light they fluoresce themselves, so which can add up the effect, thereby leading to a false positive. Or there are compounds which are known as fluorescent quenchers, which inhibit or decrease the fluorescence, like flavonoids are there, they are very good fluorescent quenchers. So, if an effect is producing fluorescence and that extract is also having flavonoids, the intensity of that fluorescence will reduce, thereby again giving a false negative test. So, I have taken an example of a thioflavin T assay. Now, this thioflavin T dye is largely used to assess amyloid fibrils in the brain, because this dye binds with those protein molecules, thereby exhibiting fluorescence. But if we are evaluating the effect of a natural product which is rich in polyphenols by using this assay, then these polyphenols also have a tendency to bind with thioflavin T, and once these molecules bind with this dye molecule, they will again exhibit the fluorescence, thereby producing a false negative effect. So, what we can do about is we can shift to colorimetric methods, but the problem with colorimetric methods is we can only use for colorless samples or light colored samples, because if the sample is dark colored, then colorimetric method will not be of great use. Then we can shift to luminescence assays. That is another remedy which one can use to overcome such kind of interference. Or we can avoid using UV range fluorescence tags, because we found that Alexa Fluor 350 red or fluorescent green tag dyes are largely used in fluorescence assay, and they exhibit fluorescence in the UV range. So, what we can do is we can shift these tags with the red shift tags, which are nothing but these are the compounds which exhibit fluorescence in the long UV range. So, if your natural compound exhibits a fluorescence in UV range, then it will not interfere with the fluorescence that is emitted by the fluorescent tag on the protein. So, such kind of interference can be overcome by using red shift tags. Another technique which we can use is T-FRET technique, and I have already discussed the importance and advantages of using TR-FRET assay in my previous lecture. Second problem we discussed, or mechanism we discussed, was aggregation. And I told you that natural compounds have a tendency to form bonds with each other, thereby forming small aggregates. And these aggregates are nothing but these are very small dense structures which are in the range of 100 to 500 nanometers. And it has been found that these aggregates normally form above at a concentration that is known as critical aggregation concentration. So, when the concentration of such compounds is above CEC, then only these aggregates will be formed. And since these are in nanometer range, these are not visible to naked eye, and such aggregates, they have a higher affinity for enzymatic proteins. They bind to enzymatic proteins, thereby giving an impression that enzyme has been inhibited, and thus they are liable for a false positive test. And such kind of aggregates, they also sometimes have affinity for other biological molecules like DNAs or other peptides, but this affinity is lesser in comparison to the enzymatic molecules. But this kind of interference also interfere with the exact result outcome of that particular assay. So, what can be done in order to overcome aggregation is the usage of detergents. So, detergent basically they will form a layer around a particular molecule, thereby preventing their interaction, and thus thereby preventing the formation of aggregates. We can also use decoy proteins, and these proteins are nothing but they will act as a decoy for aggregates, but they will not interfere with the activity of the actual enzyme, and therefore such kind of decoy proteins should be added before the addition of test compounds. So, they will block the active sites of the enzymes which are liable for adsorption of the enzyme onto the aggregates. Therefore, these enzymes will not get adsorbed onto the aggregate, and also their actual activity will not be affected. So, if your test compound has an inhibitory effect on the enzyme, that will come because the active site or the biologically active portion of the enzyme is still free for the test compound to act upon. Then we can also use high concentration of enzymes. By using high concentration of enzyme, we are producing a dilution effect onto the test compound. Also, it increases the competition of the test compound for the protein surface, thereby preventing the aggregation or the absorption of the protein molecules. We can also use less concentrated test compound solutions, and we have to select that concentration which is much below CEC. Once that concentration is achieved, aggregates will not be formed. So, these were few remedial steps by which we can overcome the aggregation. Third mechanism was the reaction of natural compounds with the thiols or amines which are normally present in the biological system. And such molecules which form bonds with these thiols or amines present in the biological molecules, we call them as covalent modifiers. And lactones, curcumin, quinones, these are certain class of natural compounds which act as covalent modifiers. So, I have taken an example wherein a study was done wherein various amino acids, as you can see in the diagram, various amino acids were used to study the effect of probe molecule onto the amino acids. Since cysteine, homocysteine or glutathione, these are some of the amino acids which have thiol group in their structure. And as you can see that if we see the absorption pattern, a lone probe, it has a very low fluorescence pattern. But when this probe interact with these three, specifically these three amino acid, their absorption or fluorescence emission was significantly increased. So, such kind of effects are observed when these covalent modifiers are present and they interact with the thiols or amines present in the biological system. So, how we can overcome such problem is by using thiol reactivity counter screens. So, what we can do is we can use a melamide probe tagging, wherein melamide has a specific ability to tag or to block those thiol groups present in the biological system. Once those thiol groups are blocked, then the test compound will not bind to them and they will the results will not be affected, and whatever results will obtain, they will be free from the interference of the thiol reactivity. Second, we can use computational models or chemoinformatic filters. We can go for in silico studies, wherein we will take the structure of the test compound and we will take the structure of the protein under for which we want to see the effect. We can see whether there is any kind of interaction on screen. We can see whether there is any kind of interaction on that, whether there is any thiol group which can interact with the molecule. So, if there are portions of the test compound which can interact with those thiol molecules, we can design a strategy by blocking those active sites or either of protein or of the test molecule. We can also go for alarm NMR studies, wherein the pattern that is obtained, the NMR pattern that is obtained of that particular extract or fraction or compound, that will be searched automatically by the software through a database, and immediately if that compound or any of the compound present in the extract or library has a propensity to react with the thiol group, immediately the screen will show you that these are the possible compounds which may interact with the thiols present in the biological system, and accordingly you can separate those disturbing compounds. Then we can design certain strategic libraries of the compounds which have high propensity of the reaction with those thiols. You can also follow a sample pre-treatment, wherein we block those active sites of the test compounds which react with the thiols, or we can block the thiol groups of the protein molecules, so that there is no interference in the overall result outcome of the assay. Fourth mechanism was the redox activity. As I told you that redox activity is nothing but the ability of the compounds to produce free radicals, like quinones are there, enones or catechol, some of the flavonoids, if they are using at a specific concentration, they may produce free radicals, and these free radicals may lead to the damage of DNA or cellular components, thereby giving false results. If we are screening for a cytotoxic compound, you may get a false positive test. If you are looking for a compound which protects the cells against free radicals, then you may get a false negative test, because the cells are damaged because of the redox activity of the test compounds itself. Remedies for overcoming this problem: we have to first understand the chemistry of the compounds which we are going to test. We can also use alarm NMRs or LC MSMS studies in order to further screen what type of compounds are present in our extract or fraction, whether these compounds have high redox value or they have a low redox value. So, if the compounds are having low redox value, then they might not have an impact on the outcome. So, again you can go for in silico studies. There are softwares, Tripos software, Syllabi 8 version is there, which can filter out the compounds that are present in the extract. The filtering means it will tell you these are the compounds which can interfere because of their redox activity. Now, what are the reasons why we miss these pan interference compounds in high throughput screening? First one is the ignorance regarding the chemistry of the panes. So, some people don't know what chemistry do these pane molecules have. Second is the lack of skill in order to identify those compounds, in order to separate those compounds. Budget, lack of appropriate budget to afford sophisticated techniques in order to characterize, in order to identify the compounds is another reason. Publication pressure has also been highlighted as a reason why normally scientists they miss the pains while performing HTS. And last but not least is the ego. These are the 5 reasons that were highlighted in a webinar, webinar of an American Chemical Society, and these were the 5 top reasons why, despite having appropriate infrastructure, despite having appropriate facilities, we still miss these pains compounds while performing HTS in case of natural products. Now, the last aspect of this lecture is how we can improve the results of HTS while using them for natural products. First one is the usage of pre-fraction of the extract. We divide the extract into different fractions. Second is the orthogonal screening, and last is the dereplication. So, coming on to pre-fractionation. Pre-fractionation is nothing, as I told you, but it's the division of the extract into different fractions, and these fractions are prepared on the basis of usage of solvents of different polarity. So, what will happen? Solvent of different polarity will divide the compounds into different fractions. Different fractions will have compounds of their respective polarity. And as I told you that pre-fractionation or usage of fraction is normally preferred over the usage of extract and pure compounds. Second is, it also helps in removing polar or the fatty material or the pain compounds. So, we know that by treating an extract with this solvent will help in removing the interfering compound. So, we treat that extract with the particular solvent. So, we remove those pain compounds and we get a extract or a fraction by which we can evaluate. Third is concentrating the constituent. When we divide the extract into fraction, then it increases the concentration of the constituent weight by weight percentage in a particular fraction. So, this will help in overcoming the effect of using a single concentration while evaluating the test extract or fractions in HTS. Then minimizing false negative due to low concentration. So, since we are increasing the concentration of the constituents in the fraction in terms of percentage weight by weight, this will also help in minimizing the false negative chances because of the low concentration during the assay. And it is always recommended to have 5 to 10 or at the max 15 fractions per extract in order to maintain the chemical diversity in each fraction. Now, this is a small example wherein the effect of extract and its fraction was evaluated in terms of proliferation and cellular health. So, if the proliferation index was less than 20%, was found to be effective, and if the cellular health index was more than 50%, then the result was found to be effective. So, if we look into the first graph, then we will see that the extract was ineffective, but when we fractioned that extract into different fraction, one of the fraction, that is fraction B, was found to be effective. So, here we can see that the effect of concentrating the constituents. Second graph shows the extract was effective and the fraction B was again effective, and the effect of fraction was higher in comparison to that of the extract. Again, the active constituent which were present in the extract, they got concentrated in the fraction B, therefore fraction B exhibited better effect. Then the third graph shows that extract was active but other fractions were inactive. Now, this graph particularly highlights the synergistic effect of the constituents that were present in the extract. And the last, again the extract was inactive and one of the fraction was effective. So, this is how fractionation has an impact on the outcome of the results. Second remedial step is the orthogonal screening. Orthogonal screening is nothing but it's the evaluation of the same outcome using a different method that is based on a different principle. It's always better to use orthogonal assay, and even the regulatory agencies are now recommending that if you are using an HTS to screen the drugs, you should also screen the hits or leads using orthogonal assays. So this kind of usage of orthogonal assays, they basically help in confirmation of the results of HTS. We evaluated say 1000 compounds using a specific assay, and out of 1000 we got a lead of 50 compounds. Now in order to confirm the actual activity of those 50 compounds, we will evaluate those 50 compounds using another assay based on different principle but giving us the same output. So in this we hereby confirming the results of the HTS. So orthogonal screening basically helps us in combating the false positives. It helps in enhancing the reliability of the results, and it accelerates the drug discovery process, thereby reducing the overall cost of the process. Last is the dereplication. Now dereplication is nothing but it's the identification of known natural products from the extracts or fractions that are used in the bioassay directly by means of spectral fingerprinting or combined with the library searching. So in this what we do is we screen the extracts or fractions and we look for, suppose you are evaluating extract against a specific activity. So what we will do, we will screen that extract using spectral techniques, and we will try to identify whether that extract have certain compounds which are already known for that particular effect or not. If those compounds are known, we will try to fraction out those compounds, and then the compounds which are not known for those activities, we can evaluate those compounds or those fractions for that particular effect. So dereplication again helps in reducing the overall cost of the process. It will also help in reducing the time that is required to identify a hit or lead molecule. So friends, these were few remedial steps by which we can improve the results of high throughput screening while using for natural products. Thank you.